Hello guys, the chapter 4 is covering the systems TT, TN, IT, and covering the RCD, RCB, MCB, and the fault calculation, touch voltages, and something look like this one. Today in the tutorial class we already cover some cases related to this topic. So when the electricity is supplied, it can be single phase by 2-wire AC or single phase 3-wire AC, 3-phase 4-wire AC. All of them I hope is clear for you. And 3-phase with 5-wire AC. So single phase 2-wire is phase and no. Single phase 3-wire, it's for the TNS system. 3-phase 4-wire means 3-phase we have line 1, line 2, line 3 and a neutral, and 5 with a earthing system, covering earthing system. There are 5 basic type of earthing as mentioned: TNC, TNS, TNCS, TT, and IT. In addition, there is an extra low voltage system for some special applications. These systems will be explained in details. So here TNC system, as you can see, we have 3 wires. We have a neutral which is done by the electrical company, here SEB or TNB. Then on behalf of N only, this is PEN, which is protective earth, protective and neutral at the same time, which is PN mentioned by here. So TNC is the worst system is the worst system in the case of the safety. Then TNS, which is the safest system we have, providing 3 lines, and neutral and PE for customers. Then we have TNCS, exactly the same as TNS, but if the customer or the electrical company utility don't have enough money to support the extra wiring, using the TNCS, which is a good system for protection. Next one, TT system, is one of the good system in the case of the protection. And last system is IT system, which usually the neutral point from utility side is not connected to the ground or using high impedance grounded. For the first fault in the IT system, there is no significant changes in the current and voltage, but if there is a second fault in the IT system, the system will change to TNC system. So please thinking about this case, how IT system will change to TNC system. TT grounding system, as you can see the system by right hand side, means you have to provide the local grounding as a user by yourself, and the utility, electrical utility, will provide you a ground. So the system is using in many countries, as you can see listed by here. The supply system is solidly grounded, very important one, solidly grounded. How can I make it? Is here solidly grounded, and neutral is usually carried out in order to provide power to single phase loads. So why we need neutral? It's mentioned by here, which are typically in dwelling units, I mean single phase users or loads. The customer's ECP are connected to the ground electrode independent of the earthing of the utility. So this is separate. This is we are talking now about RG, not RN, about the G side. In this condition, the ground fault current will return to supply through the soil, means the earth, flowing through both the earthing electrode and the installation RG and the earthing electrode of the source, so RN. So if any fault happen in this system, as a result, the grounding fault current is limited in magnitude by the two above mentioned earthing resistance. So RG and RN, as today in the tutorial class, hope you saw, the RG and RN limiting the fault current. So bigger RG and bigger RN, low faulting resistance. Therefore, RG is independent of where the ground fault occurs within the system. TT system is free location for the fault because there is no significance of a phase and neutral or the PE cable, what we call it, impedance of conductors. TT grounding system are used when electrical utility cannot make available safe means of earthing for their users. The owner of the installation therefore must provide its own connection to ground supply, apply suitable earthing electrodes. So all based on the end user, the customer. As you can see here at the right hand side, the system TT system, which here again washing machine and the PE cable, this is the phase. If I start, so upon grounding fault, persons conservatively assumed as standing on the area at zero potential are subject to the touch voltage caused by the ground current IG. So ground current here. So RG total, which is represented by here, is RG, ground resistance, RPE, PE is this one. Then there may be cases when the ground resistance RG is very low, that is in the same magnitude of RPE and RGCE. So at this time we have to consider these two terms. In addition, we can reasonably assume that the internal impedance of the source and impedance of the phase conductor are negligible, as I mentioned before. So in low voltage system, we conservatively consider persons exposed to prospective touch voltage VST. So by this introduction, we know, as you can see the circuit on the right hand side, the magnitude of the VST is equal to V phase, which is by calculate the value for the VST. The negligibility of the phase and protective conductor impedance shows that the location of the fault, which is directly related to the phase and protective conductor impedance, has no influence on the magnitude of prospective touch voltage. So again, this one mentioned by here. Therefore, VST is constant value regardless of where the ground fault occur, but does depend on the system ground resistance. This is very important. So RG and RN, here RG and RN distributor means utility are very important in this case. So here is example how we calculate. Again, I mentioned this one in the class, we covered this one again. Here RN and RG given. RN is 10, RG is 50. The system is TT, and the voltage given is 230 here. Okay. So VST, voltage across this one, as I mentioned, how you can do the voltage division can be calculated, and the VST here for the RN and RG 1050 equal to 191.67. But if we reduce the value of RG and R if we change the value of RG, means make it more conductive, reduce it to 10, VST of course reduce to 115. Then based on this system, the second value, if somebody touch the ECPs, which the voltage across that one is VST, you can calculate the VT here. This is not VST, I think this is wrong. Which is equal to RGT equal to 10. This is equal to this value. So in the exam, if you consider the the RB plus RBG, such as here, is quite bigger than RGT, no need to calculate RP, because if you calculate based on my technique, which is ignoring RP, the value is 87.2 or 0.3. So it's not it's around 0.5 half volt difference for this one. But if you consider as the same as here, it mentioned in this slide number 15, if we usually ignoring RPE and RGCE or ZI and Z phase, but in the case that the value is close, you have to consider the case for more accuracy. So here also, if you're ignoring the value, not changing so much. Thank you for consideration.